Okay, dear colleagues, here we are again in the microwave seminar. So today our speaker is Dr. Leonid Grunin, who is a managing director of the resonance system. So from the Germany. So Leonid, please start.
We speak English? Better? Let's do it in English. Well, I feel really high honor to participate in such an event. Mikhail just described me how important this university is in St. Petersburg and in Russia. So that's why I feel extremely excited. Well, about our today talk, I actually would expect it to be a kind of discussion. But for this discussion to start, I would like to give an introduction of what we do, what area of investigations of engineering we work in, and then we will try to figure out our common interest about all that. So just very brief history. I graduated from this university in Yoshkar-Ola in 1995 and made my PhD in physical chemistry in 1998. For that PhD, I had to build own instrument of magnetic resonance. We call these instruments relaxometers. This is not really a spectrometer. This is a relaxometer because the main target of that is to observe the relaxation, not the spectral resolution. And actually, we had a kind of experience in our university building own devices for 30 years before. Everything is originating from Kazan State University, where in Kazan the magnetic resonance was discovered experimentally first in the world in 1944. So this scientific school is coming from Kazan State University. I want to talk, we will talk today about magnetic resonance and time domain magnetic resonance, and what is the difference and what instrumentation can be utilized. Anyhow, all these methods are analytical methods, and we all work for chemistry, mostly for chemistry, for chemical applications, to do analysis, to understand what is the structure, what is the kind of dynamics of our samples. So, and analytical methods can be chemical and can be physical. Chemical are not interesting to us at all because you need to do some mixtures, you need to do classical chemical stuff. We focus mostly on physical methods that don't require knowledges of chemists. Out of many different physico-chemical methods, we select spectroscopy. Then out of spectroscopy, we select quite narrow range of frequencies that can be attributed to nuclear magnetic resonance. So in fact, for time domain, it is between time domain NMR, it is between very low field, a kind of, you can get the NMR signal even in the field of our planet. And let's say the upper border of time domain magnetic resonance is normally restricted by the power of permanent magnets that are now mostly used in NMR relaxation. If we talk about, so this is the time domain, this is very narrow band. Actually, big guys like Bruker, they are building very strong superconducting magnets that can reach, let me calculate, 30-40 Tesla. Really strong fields, and then inside these fields are really required if you want to get a spectral resolution and want to investigate long, complicated molecules. Well, but let's go on with the time domain. So primarily, magnetic resonance, nuclear magnetic resonance, can be subdivided mostly in three different directions. One is the high resolution spectroscopy, which is actually known for most of people. All chemists, they study NMR in their chemical courses, and they think that NMR is the high resolution. This is spectroscopy, when you can get the spectrum and you can get the information of chemical structure. There is also low field relaxometry, which is time domain that we will talk a little more today. And also there is imaging. Imaging gives you spatial resolution. So you can look at different dimensions. You know that because we all live in the 21st century and MRI is everywhere. So, well, very briefly, can I stand on that? Yeah, might be some interest. So, okay, we have the magnet. In this magnet, we place a sample inside this magnet, and let's say quantum physics. If you have the nucleus of, let's say, of simple hydrogen, you apply the field of 1 Tesla, and you get frequency 42 megahertz. This frequency is not high, it's not low, but this frequency can be somehow detected. So when there is no field, the spins, they don't have the Zeeman effect. When we apply the field, we get the splitting of the main energy level, and the transition frequency is just proportional to the magnetic field. To do analysis, there are several things that influence this frequency. Let's imagine we have the very homogeneous magnet, and then we are talking about nuclei. All nuclei, they have this, they are self-magnetic moment, spin magnetic moment. This is a kind of magnet, small magnet, and they try to align along the field or opposite the field. So this is the local field that they produce. Also, each nuclei have their own structure of electrons, and these electrons are being influenced by the main magnetic field that is produced by the magnet, and these electrons start to shield this field, and they lower this field on the nucleus. So the frequency of the resonance, if it was 42.577, if we apply and we have some nuclei with the electrons, just any kind of water or ethanol or anything, these electrons slightly, for some ppm, are shifting the frequency. So, and the difference of frequencies depending on the structure can give the information about the chemical structure. Let me show you. Well, if you take simple liquid, it has 3 different chemical groups. They are different because they have different structure of electron clouds. And this structure of electron clouds is influenced by the magnetic field and produces the shielding. So, and the shielding is called chemical shift. So for CH3 groups, chemical shift is about 1 or 2 ppm. For CH2, it's about 3 ppm, and so on. So having kind of spectrum, you can get information about chemistry. That is why the high resolution spectroscopy, so NMR spectroscopy, is being considered as one of the most effective method for chemical analysis. And the amount of Nobel prizes somehow connected to NMR is really higher than for any other branch of science. So this is not the topic of my lecture. This is just how, if you someday will be interested in chemistry, how to use the NMR spectra. But talking about time domain NMR, we don't need to have really complicated hardware. We don't need to maintain extremely homogeneous magnetic field. You can build the magnet by your hands, and this will work. And this magnet produces more or less somehow homogeneous field. You put just the coil, and you put, just imagine, we have 1 Tesla. We put there a kind of sample that contains hydrogen nuclei. We give very strong pulse, really strong pulse, hundreds of watts of radio frequency, exactly on 42 megahertz. After the pulse, all these quantum effects will take place, and then the relaxation starts, and the relaxation must be detected by the receiver. Here I already start to talk about the technology. So magnet must be somehow homogeneous. For high resolution, it must be very homogeneous. Transmitting pulses, excitation pulses, they must be extremely strong. And the reception pulses, acquisition. So here on normally you build a kind of resonance circuit, and the voltage during the pulse on the coil can reach a few kilovolts, really high voltage, and you need to use very expensive capacitors, otherwise they will be just broken immediately. So out of some kilovolts, you get the reply. Yes.
Zoom, they don't listen to you because you should. Yeah, sorry, you should put your microphone in this
sure.
manner in order that
is it now okay?
In Zoom, yeah, they should listen to you as well. So
yeah.
People in Zoom, do you hear us well now?
Mm-hmm. Okay.
Yes.
Okay. Yeah, I'll do. Well, I was thinking we were talking about voltages. So here from the transmitter, kilovolts, here we have microvolts. So that's why these devices were really not easy to build. Now the technical progress and technology is evolving, and we can see many changes. So these devices are becoming more and more available, more affordable. It means that you are able to use it more. So I think I will not talk about magnetic resonance. If any questions arise, I will talk about what we are doing. So what we are doing, we are applying the radio pulses, and then we are playing with the magnetization of a sample, macroscopic magnetization of a sample. That is a composition of each of billion of contribution of these microscopic spins. And during measurement, we see two types of relaxation: spin-spin relaxation and spin lattice relaxation. So these are already two numbers that you get from the NMR relaxation. And the behavior of the magnetization can be described with a quite simple equations, vector equations. And the result, you normally see the exponential decay if you have quite simple structure of a sample. Exponential decay for T2 for spin-spin, and exponential decay for T1. Well, for example, if you have a kind of sample that contains two different phases, just imagine you put anything, you put your food, you put your bread into a test tube, and you will see at least two contribution for water and contribution from the lattice, from the rigid lattice. You can imagine immediately measures some stuff. So now I'm trying to come more to technology. So, well, the advantages of time domain is that it is not expensive, but it is still an NMR, and it is giving you things that normally cannot be measured by the high resolution NMR due to, for example, interaction, solid state interaction. Well, talking about evolution, some of us remember guys like this, and the computers that were somehow spread in the world 20, 30 years ago, they were built for specialists, and they were used by programmers. That's why that was that was not normal for just ordinary people to operate with computers. Now things changed, possibilities are growing, and a computer now every one of you have computer, and everybody is using computer. So this is the trend of common progress. The same is happening to NMR. All the devices, you had to be chemist, you had to be electronic, you have knowledge in electronics, in programming, in lots of things, and also in magnetic resonance to operate it. Now, these are just screenshots from the main conference on magnetic resonance. Now, people are just using software. They are studying a little bit with the kind of bars and anything. They don't need to know electronics. They don't need to know signal processing. They just use the program, and the program gives them information about chemistry. So everybody is coming to NMR now. I don't know whether it is good or bad, but anyhow, this is the situation we have today. And the requirements for instrumentation is also changing. Of course, we are now in the academia institution. So we are talking about investigation measurements. We can talk about laboratory equipment, but let's say the main vast flow of equipment, of measurement equipment, is done not really for academic researchers, but for the results of academic researchers to be implemented in industry. But in the industry is requiring what's happening. Okay, somebody. So everything is moving to miniaturize, to have a common interface and so on, and be available. So this is a general trend, and this is the trend that we are participating as a German company now in this trend. Nevertheless, it's still very important that there are still some scientists and people who are pretending to be scientists. Oh, doesn't work. Typical guys that are used in industrial applications, not in academia. They are all NMR. This guy is done by my friend, not Juan Perlo, friend from Argentina. He now, Pablo Prado, he lives in San Diego in America. And they are producing the guys to analyze, to do the custom clearance of goods. You know, when you build a kind of NQR device, it is sensitive to nitrogen, and you can detect both explosives or drugs, strong drugs. So really interesting guy. So this guy is specially done for analysis of fat. It is just very small. You put the test tube with a food product, and it gives you in some minutes the total amount of fat inside. So this guy is multi-nuclear. There is a magnet and different sensors. The Norwegian people, and actually it's quite cheap. It is $12,000. You have the sample that is flowing inside and then getting out, and it is measuring the content of different nuclear, different isotopes. For example, aluminum, phosphorus. What else? Fluorine, hydrogen, so many different nuclei. So this is the instrument that we used to produce some years ago. It is installed in Korea. I would mention this guy. This is produced by a Finnish company, Valmet or Metso. Where is Metso? Let me show you. Talking about the boards, talking about, so we are selling our boards to these Finnish people. We already provided, I think, 70 boards. Here you can just see the industrial applications of time-domain NMR. They have their own magnet, electromagnet, 750 kilohertz. Such a big magnet, and they put there, you will see. Yeah. You know, Finland produces electricity out of wood. They don't have gas. That's why they burn lots of wood. Actually, we can look it forever. Let me just see when we can. So the more water we have a sample, the less typical Kayani picture.
All these NMR Time-Domain NMR instruments, they are actually sold to industry and they use it like day-to-day application.
Yes. And they're using our boards. This is what people need. Simple. Everything is very simple. I don't think. Well, so okay. Yeah, I guess yes.
Thank you. I'm wondering if you need an RF shield to operate in that case, or do you need a special room?
There are many types of shielding. There are many different types of shielding. If you talk about the probe, the sensor, then you have the coil. The coil likes to capture everything, and this brings lots of noise. And also it can catch different signals from electricity, from everything. Of course, we are using cables, RF cables, normally semi-rigid cables with a good shielding, and the probe itself must be also shielded. Shielding is critical. So I think good question. We will come soon to definite things about the technology, and then we can make the kind of interactive discussion.
Okay, thank you.
You mean about the Valmet?
Yeah.
About
So it looks like they bring it to a certain room.
Let me tell you, if you are talking about MRI and you have someone who is going inside the magnet, these people are not also shielded, you know.
Sure.
Here you have very close situation.
Okay, so you can close some cover.
No need to shield it from upstairs.
Why?
Because actually, you know, the bandwidth of the probe and the bandwidth of the preamplifier is about 30 kilohertz. It is quite narrow band. Then you know your noise is proportional to bandwidth. Bandwidth is narrow. That's why if you close it, so most of the noise is already somehow outside. If you shield it from upstairs, you will get the improvement, but that improvement wouldn't be so much important for the situation.
Okay, then for the reception it is clear, but how about the opposite direction? If the coil transmits, so you said you apply quite strong voltages. How does it affect the outside equipment and some other devices?
Well, let me tell you about this instrument. You put sample in this direction. The magnet generates the field in this direction, and you have the spiral coil. The spiral coil produces the radio frequency field, and this field is but I think you have seen that the lady, she was putting it quite deep.
Okay.
So just outside, I think if you put there a special device that can measure this radiation, you can get it. But you know the duration of a pulse is a few microseconds. So it normally doesn't bring any problems. The same we have back in MRI. When we are going inside the magnet, we are experiencing strong pulses, but nothing is changing because the energy of these pulses is really low. This is the lowest energy in all spectroscopical methods. Even the sunlight is stronger.
Thank you.
for some other systems, and that requires you to have very good shielding, like legally.
It used to be many years ago, but now all this communication and GPS and mobile stations, they are in gigahertz range. We are talking about megahertz. We are talking about tens of megahertz. That's why there is nearly nothing. And you know, it used to be when it was Soviet Union, we all liked to tune to short waves and listen to Voice of America and Radio Freedom. Now it's not possible to get any, so I take the same receiver, I try to find these stations, but nothing, everything moved to the internet. So even the long waves, short waves, they are killed. Of course, you have frequency modulation radio, FM radio. They do, and if you are close to the antenna, you feel it. Definitely, this is clear.
So the room for that device doesn't need to be shielded.
Oh, no. There is shielding inside. There are many different shielding inside.
Okay.
But this device complies with the declaration of conformity. You know, the sign of CE on many instruments, on each of your monitor, each of your mobile phone, you have CE. It means they fulfill the regulations of European community to protect people from any kind of harm. So all of these guys, they have the CE mark. Everything is safe.
Yeah, thank you.
We can talk about this actually later. So let me now switch to what we have done. So I have built my first NMR in 1995. It was built on absolutely Soviet transistors, chips. That was really funny, but that was working. In 2000, I managed to somehow enter a Blumich group in Germany, and we started to work more effectively. So this is something that, like our instrument, looked like 20 years ago. The question about shielding is actually more important for this type of instruments. This used to be named NMR mouse. Mouse can be abbreviated as movable universal surface explorer. This idea came to German professor Bernhard Blumich in Aachen in 2000, and he decided to build the guys. So the mouse itself, it contains inside, it has U-shaped magnet. So the one magnet is producing field upstairs, the other magnet is producing field direction to downstairs. And here you can see the radio frequency coil, surface coil. It's nearly done as printed circuit board. And here are two magnets. If you put something on top, you can measure NMR relaxation. The homogeneity of device is really poor. Nonetheless, you have the ability to measure NMR. This is actually the cheapest way to build NMR sensor, NMR probe. And of course, this guy likes to capture all noise and all these radiations. That's why it's very important. If you want to have the precise measurement, you put some kind of copper shielding onto it. So these guys are from 15 to 25 megahertz. From 15 to 25 megahertz. Simple guys, coil, capacitors, two capacitors, and the magnet. Then this is something that we built later. Not really nice. So we have built, I think, hundreds of different solutions. We like to work both with universities with interesting projects, and also for industry, because we need to earn money. So one of the really interesting projects was done with an interesting guy, actually David Sistola. He investigated the relaxation of a blood plasma. And he captured data from, I think, 20,000 people. And out of this database, he analyzed who of them got the diabetic disease after. And based on the analysis of the relaxation, he was deriving 2 or sometimes 3 components from the relaxation curve with the different relaxation times. He built the model that can predict whether you can be whether you are in the risky group for diabetes or you are not in the risk area. And so for him, we built also the magnet that is not really shielded because you are able to put your finger inside. So now he's writing papers and then talking to the different conferences. Here is the, let's say, the reference. Very interesting project and very useful, by the way, for people. You can put their finger, wait 30 seconds, and then the system predicts whether you are in a risk area or not. Another project we have done here in St. Petersburg, interesting project. It was done with a MRI machine, but it was not really MRI. The idea was to build a device that is sensitive to natural abundance of deuterium H2. Where is it written? Deuterium. It's not visible. It's
Leonid,
upstairs.
sorry, we have a question from the chat.
Okay, yeah, let's answer.
How accurate is it? Sugar level measurements.
Accurate
It's probably regarding the previous slide.
How accurate the relaxation measurements are quite accurate. We are working on reproducibility and repeatability. It means when you have the same finger with the same temperature and you put it there, so and you measure it 10 times, the standard deviation of measurement is definitely before 1%. Normally it is 0.4%. The standard deviation of 10 measurements of relaxation times. But if you hit it your finger, immediately you'll get a different result.
Losha, is it okay? Is it clear?
I think the question was about if it measures the sugar levels in the blood or if
you know, the composition is extremely complex. There are so many guys in the blood, and especially in your finger. Of course, we don't capture bones, we don't capture nails, we don't capture skin. We capture mostly liquids, mostly blood, and of course the composition of blood is also complex. It somehow is talking about sugar, but there are some precursors. The guys that this is not really sugar level. I think for measurement level of sugar, you can use much cheaper instruments. Okay, are there any more questions in chat?
In principle, is it possible to apply for blood sugar level as well? Because everyone wants to have a non-invasive method for measuring. Therefore, maybe it's not a bad idea if it is possible.
You know, we are detecting. We are working on here on hydrogen, so on H, and this hydrogen, if something is changing with the mobility or molecular mobility, then you can see the difference in the relaxation times. We have lots of experience of measurement sugar in food. Mm-hmm. In principle, you can build the calibration, but only in model system. This is not the case. You measure precisely your sugar level, unfortunately. On the other hand, it's possible if you build the high resolution NMR, then you can just look at spectrum and find the glucose contribution into spectrum. But you know, this will be very different money. And I'm not sure that now it's possible to build such a device that you can put your finger without cutting. Mm-hmm. So the idea is great, but not yet.
But what do you mean high resolution NMR? Does it mean you need more signal?
High resolution, you need to have more homogeneity of a magnet. The homogeneity must be perfect. It must be far below 1 ppm. Mm-hmm. The time domain magnets, they are just cheaper, and of course the level of the field strength we are talking about normally from 0.5 to 1 Tesla magnets, and in high resolution the higher field the better.
Mm-hmm. Thank you.
Well, so one more interesting application, you know, if a patient has a kind of cancer cells, they like to absorb the liquids that are being taken by a human faster. So we differentiated the breast cancer of ladies. We spent many nights in MRI centers here in St. Petersburg, and we really discovered that. So that just lady is lying, and there are two coils on two breasts, and we are measuring the signal of deuterium. And this lady is taking very small amount of a kind of heavy water with a low concentration, and in 5 or 10 minutes we get the rise of the signal initially, or so this is going much faster. Rise on the signal in the tissues that are corrupted by cancer. Really interesting project. Now, unfortunately, it stopped because it should have more money. Nonetheless, it's interesting. So I can talk a lot better, answer your questions. So this is how our instrument is looking now. So this is something that we bring new to the market. Very small guy. It's now the first release is already done, and you can program any pulse sequence. You just put the test tube and you measure it, and you get all the results either on the screen or anyhow. So this is the kind of our MRI that we managed to do ourselves in handmade magnets. So if you want to build the MRI, it's really possible. Well, now this is a kind of starting of discussion. So having experience of building a company that is producing magnetic resonance instruments. So I have subdivided into hardware skills and software skills. What is needed to build the instrument? So you need to first build something that is producing signals, generating signals of different frequency shapes and pulse sequences. And it is normally based on FPGA technology. To generate signals and then get the signal, that now there are no analog receivers at all because they are not competitive at all. So you use the high-end A to D conversion, high-end D to A conversion, and all the rest processing and generation is happening on the FPGA board. This is something that we can talk a lot because I do this job myself. So analog power amplifiers, strong guys that produce sometimes up to kilowatts if you want to deal with a big MRI, and up to, let's say, 100 watts if you want to deal with a small test tube of 5 mm. Low noise amplifiers, another demand. To be competitive now, you need to have the noise figure. You know what is noise figure? Noise figure, this is something that your amplifier is introducing into the signal. The noise figure must be below 1 dB. This is really low noise figure. It was not possible before to do such a things, but now to be competitive, you need to produce such a guy.
Thank you. I have a short question about analog amplifiers. So you say that for MRI, for large volumes, we need somewhat like kilowatts. Yeah, kilowatts. And for 5 millimeters or 10 millimeter tube, you need hundreds of watts.
100 watts. Or if you want to work with liquid and you are you feel okay if you have the RF pulse, the 90 pulse of, let's say, 100 microseconds, then you can use 10 watts.
10 watts. And say if I want to build like really tiny samples, maybe a few millimeters, how much, what kind of amplifier would I need?
A few millimeters, what do you mean by few millimeters?
A few millimeter in, like, say 1 millimeter in diameter.
Okay. If you want to, again, work with liquids,
yeah,
because liquids, they don't require short pulses. If you want to work with liquids, the high resolution system that we built together with the Israeli people, we used 8 watts there. The pulse was 100 microseconds. 90 pulse was 100 microseconds. It was 8 watts. On the 10 millimeter tube, I think on 5 millimeter tube, you can use even 4 watts. You will get a kind of reply. Well, low noise This is very important, very critical. Then if you are working with permanent magnets, you must stabilize the temperature because your magnet is drifting, and normal drift for neodymium magnet is 1000 ppm per 1 degree. So you need to keep temperature. So we now stabilize temperature to 0.002 degrees centigrade. And it's more or less good for time domain, but it's nothing for high resolution, by the way. Also to temperature control for magnet, also for sample, because sometimes we want to measure temperature dependence of relaxation. Pulse field gradient generation. This is for MRI and this is for diffusion measurements. And you need to have high currents amplifier, and this amplifier must be extremely stable to do. If you want to measure diffusion, the requirements to amplifier are just fantastic. You need to design magnets, to design probe with the right shielding, of course. You need to do shimming. And now what's important, this is what we are doing actually. All these industrial applications, they now don't like to work with humans. That's why there must be an automation solution for Internet of Things, for cloud technology. And also you need to write some software thing that I just enumerated something. So this is all that we are doing in a resonance system at the moment. And I used to, so all people who are working in the resonance system, they actually are all my former students. But now I stopped this academic activity, and that's why it would be really interesting if someone can be grown up and join us. And we are searching for intelligent, clever, and let's say motivated people, just to start talk about things. This is what we get inside the FPGA board. If some of you are thinking about building your own spectrometers, we can talk about that. Oh. This is one of our boards. This is actually MRI board. 2 receiver channels, 2 transmitter channels, and 3 gradient channels. There are different configurations. Now I'm just showing one of them. Well, actually, that's all I wanted to talk. This is just the beginning. Let's discuss.
Yeah, so my question, it's just simple radio frequency question. So how you divide, receive, and transmit signals if you use one channel coil? Like so
how we divide signal between
transmit and receive if you use one channel?
Yeah, there are lots of different solutions. Normally, this switching, it's not division, this is switching.
Yeah, I know.
This switching must happen really fast and must introduce as low noise as possible. The universal solution is based on pin diodes or just diodes. When you have the diodes and you put the reverse voltage and then the diode is closed, right? And then you can somehow switch. Anyhow, these guys are connected to filters and they introduce ringing. In our situation, there is a classical NMR solution, lambda divided by 4 cable. This is a kind of long line, and if it's short on one side, it is open on the other side.
Yeah, I know. So you use TR switches with lambda over 4 elements. So and what typical losses that your device introduce?
So we are not using this type of solution. We are using just filters. We are using low pass filters, and these low pass filters and they involve cross diodes. If you are working with a strong signal, these diodes are considered as short, and then you get the parallel contour that gives you really huge impedance, and signal doesn't go through. And if you are working with a low signal, then this parallel contour turns into just low pass filter, and this low pass filter lets the signal come through. The loss is not really high; it's about 15–20% in the worst case. But this type of switch is most optimal. It's used by us, used by our competitors. This is something that people are living now. There are guys in America, the company TechMac in Houston, in America. They have developed their own switch, really wide range switch. The switch, the duplexer, we call it duplexer. Now like this duplexer is for quite range frequency band, quite narrow frequency band. So for you to have this kind of resonance conditions. So there are guys who are doing this on pin diodes, but this actually I don't like this solution.
Why? So the typical losses of pin diodes switches.
I can tell you. Working with liquids, it's actually doesn't matter. Working with solids, my main scientific interests they are in the NMR relaxation of solids, and we are dealing with extremely short relaxation times. And the process of switching brings the oscillations not from the sample, but also these artifacts from these coils, from capacitors, and they are spoiling the initial decay of solid state NMR. That's why I don't like them. So this is just, and we also use them for very low signals for NMR mouse with those surface sensors. They really introduce really more noise than the low pass filter.
Yeah. Okay. Yeah. Thank you.
So, dear colleagues, do you have any other questions?
Yeah, thank you so much for very, very interesting overview. And could you maybe tell us something about the activity of the company right now? I mean, what in general are so you have shown a couple of products you put to the market. So there was this large device for applications like in Finland.
So this guy, the self cost, I can tell you. So will it be published? Yeah, because that's important not to tell to competitors. The self cost with the materials and with the manpower, it is 3.5K euro. Then you need to have some. So we can sell it. We can sell it for quite a low price. We have competitors who sell such a guy, of course, with 5mm tube and worse signal. They sell it for $10K in America. Telatomic and teach spin. Honestly saying, this device has lots of capabilities, nearly like the spin check that I showed here. The only thing we cannot vary the temperature of a sample, and we don't do the pulse gradient inside. All other stuff, all other features are included. We will bring it to the market, to the high price segment for in the industry, and of course we will bring it to academia.
But what could be the final price for the university, for example?
We need to look at the market. You know, this is actually not, but my estimation, it will be below 10K euro.
Okay, thank you.
And we have a question from the chat from Dr. Alexey Slobozhenyuk. What do you think about low field human MRI below 0.5 Tesla in terms of global market perspectives?
Well, below, it depends of type of application of human MRI, because sometimes you don't need to have high resolution in your picture, and you need just to detect some pathological things. That's why 0.5. This is a classical MRI machine that was really popular in recent years. Now things are changing to 1.5 Tesla, but 0.5 Tesla is not the low field MRI. So we have done, you can see at this place, how to come here. We have done this image. So this is the fast image. This is the image accumulated. So this image was acquired during 1 minute. This is the piece of a plant, and we see water. We don't see wood inside, right? We don't see the cover, but we see it was just cut from the tree, and you detect the water here, and then when you do more precise investigation, you get the. So this is done with, I guess, 17 megahertz. This is below 0.5 Tesla. So this is possible. This is really possible, but once there are so many applications, so many 1.5 Tesla or 3 Tesla machines now. So I think the market And the people who work in the market, you know, this medical stuff, they normally don't know the basics of MRI. They know just the applications. That will be the great problem to educate these medical stuff to work correctly with 0.5 Tesla. So
question was below 0.5.
Below, so
yeah.
I mean, what is below? If you below 0.5, this is already a problem. Well, this image is done below 0.5, but this is not human. This is very small, very small sample. I think the main problem is not in instrumentation. The main problem is just in bureaucracy and in the market. This is the question. So no one is interested to buy and to sell for cheap price. This is something that is moving the consumer society, unfortunately.
So maybe I have a question. Can you please go to the slide with hardware and software?
With what?
Hardware, software.
Okay. With a list.
Yeah, so my question is, what are you doing in your company in hardware, software?
We are doing all this stuff. Yeah.
By yourself.
Of course. And I don't mention here the NMR application. This is also what we do.
So, and you have 12 people, right?
We have 12 people in all. Some of them, they do NMR. Some of them, they do accounting and bureaucratic. They're mostly Germans. And all Russian people are doing all these developments.
So you're purchasing just some components and doing everything by yourself, right?
Well, no. When you produce instrument, you have to comply with this declaration of conformity, a lot of standards. So we are not able to produce now PCBs by our hands of such a. We are ordering printed circuit board. We are ordering parts of metals. So assembling is being done in Germany or in Russia. Assembly. But this is an engineering job. This is development.
Software.
Software, we have two people for software, my friends and I. We are writing software together, and I work with all these topics also with other guys of my company.
Okay, thank you.